Okay, so welcome to my first Watch Me Study episode. Um, Today's video I'll be doing my non-metals chemistry, and so yeah, just sit back, relax, and just see my thought process when I study. This video is just sort of kind of helps me focus to study as well, motivates me to study a little bit. So yeah, feel free to speed it up or do anything you like. Yeah, I'll just get started. Okay.
Tí cưng làm xong đó chị nhỏ chưa tí.
Hả rồi.
Cưng không dẹp lại luôn đã đó.
So let's talk about the trends. So I'm just move this right over here. Right, so trends. So if we go down, this is 2, n equal 2 here, n equal 3 here for the periodic, for the rows, for the periods. So if you go down, you decrease electronegativity, electronegativity. You increase atomic size. So why? How is decreasing electronegativity significant? Probably. So that means if you decrease electronegativity here, then maybe in a, say, PO43 plus compound, the oxidation state for P will be positive, and oxidation state for O will be negative, because O is more electronegativity than P. So I guess that's why it's electronegative. In terms of atomic size, what do you get when you have a larger atomic size? I know that one of the impacts is that it won't be able to pi bond, do pi bond with itself or with other elements. Even if it does, it's quite rare. So we have to go here, and so this is the ability to buy pi bonds. Okay. Because if you're too large, then the pi orbitals won't be overlapped really effectively. So that's probably why. Is there anything else? If I can't remember, I'll have to look at the notes. Size, pi bonds. Yeah, okay, so the more atomic size, large atomic size, the more orbitals you have. And because the more orbitals you have, you can essentially increase this. Actually, I'm going to redo that. You actually can form more bonds, more sigma bonds. Okay. Another thing is oxidation state. This group here is 14, 15, 16. So you got 4 valence electron here, 5 and 6. Also maximum oxidation state will be 4 plus, 5 plus, and 6 plus. And so what that means is, because you have 4 valence electron here, 5 valence electron here, and 6 valence electron, you will lose all of them, and you have 4 plus, 5 plus, and 6 plus respectively. So that's so far for the electronegativity. Let's compare each and single one of them. Okay, what can I remember in terms of possibly structure, reactions? I think I'm going to compare it in terms of structure first, in terms of, let's say, natural form, and in terms of so this is probably physical, and this is probably chemical, how it reacts, and that can be in terms of oxides, hydrides. C, I'm pretty sure C and Si here. We'll do one for that. We'll possibly do, okay, so C here, Si there. Natural form for C is probably, I think C has 3 carbon allotrope. Yeah. One is graphite. So in terms of allotrope, you have diamond, which is a covalent network. Covalent network of carbon. We have graphite, which is like parallel sheets. Okay, so I'm gonna go sheets. That's my sheets of carbon lying on top of each other. And the last one, I forget. Oh, sorry, there are only 2 allotropes. There were 3. Fullerene. So 2 in graphite structure, 2 of them make 2. I'm just searching up on why graphite has pi bonds. So in graphite structure, 2 of them make 2 single bonds. So essentially, carbon has 4 electrons, right? These 2 here forms a pair, and that's helped form a pi bond with other carbon, and these form sigma bonds here, and that kind of just possibly stabilize the structure, link everything together. Yeah, I'm happy with that. Fullerene. In terms of silicon, it has a diamond structure. Yeah, so on diamond cannot be so chemical properties, catenation, Oh, I forgot. So allotrope. What is catenation? Catenation is the ability of element to form bonds with each other, and maybe the different ways in which they form bonds will result in allotropes. Catenation forms bond with itself, with elements, with atoms, or same elements. Okay, cool. Oxides. Carbon form carbon dioxide. Carbon dioxide. 1, 2, 1, 2, 1, 2. Wait a minute. How do I draw a Lewis structure? Carbon has six electrons. Oxygen has 8 electrons. So we have 14 electrons to fill. So 14 now down to 12. 1, 12, 10, 8, 6, 4, 2. Wait a minute. 2, 4, 6, 8, 10, 12. Carbon has 4 electrons. Oxygen has 6. Oh, oops. 10. They have 10.
Để con đợi cái thằng kia nó khô rồi đem vô.
I'm so confused. Carbon has 4 electrons. Oxygen has 6 electrons. 4 plus 6 is 10. Carbon monoxide. Carbon dioxide. Oh, carbon dioxide. Okay. Like that. So add another 6 is 16. I'll just do that. Do that. Do that. Do that. 2, 4, 6, 8, 10, 12, 13, 14. Yep. And then carbon monoxide is 10. So 2, 4, 6, 8, 10. Here we go. Carbon here, oxidation state for carbon is -4, is +4, because the oxygen are -2 charge, and the carbon here is +2 charge. Okay, that sounds like it. Hydrides go down here. Hydrides, you have hydrocarbon, in which case oxygen carbon will be like +4 charge if it's all bind to other carbon. Not sure. In terms of chemicals, I'm pretty sure silicon forms silicon dioxide. So that looks again like that. And I'm pretty sure they also exist in total equivalent network to form glass. And it looks something like that. So Si. Is it? Yeah. Okay, that's interesting. Yeah, so normally silicon dioxide exists as that. In pure oxide silicon, it is also made, it is then linked with other silicon dioxide to form this covalent network of pi bonds. And as a result, the covalent network will be quite So it will exist as a solid, whereas that will exist as a gas because of the intermolecular force. Okay, so molecular force cover the network, so this will exist as a solid. I'm actually going to do that in another color. Solid and will be gas. Gas. Okay, it's because this is governed by intermolecular force, whereas that one is intramolecular force here. So they exist as a solid because they're quite close to each other. Force. Okay. Silanes. Alright. That's it, I think. Yep. Let's talk about these guys over here. That's a good summary here. N and P. Okay, so N versus P. Okay. Allotrope. Oh, I also have to talk about nitrogen reaction as well. I'm gonna put down here. So reactions involve nitrogen and more specifically nitrogenation. Okay. So natural form of nitrogen is nitrogen gas. It is quite inert. And so to break it down, you need like a variety of different mechanisms. Whereas P, it exists as P4 and P. I think just it exists as P4, but you have white and red sulfur. Also, so the effect of electronegativity is on the oxidation state. So what that means is that for carbon and silicon, they want to lose electrons. It's like half-half. But for NP, not only can they be positively charged when hanging out with a more electronegative atom such as oxygen, I think mainly oxygen. If they're hanging out with hydrogen or and something that is less electronegative, they will carry a positive charge. So things like ammonia. For phosphor, I couldn't see one phosphor, but if they hang out with hydrogen atoms that are less electronegative, nitrogen and phosphorus will like to have that electron, so they'll become negative. So things like cyanide, ammonia. Okay, that's a good point to make. So I'm just gonna go. Yeah, you got P4. It's either P4 or P4 polymer. This is white and this is red. So the reason why, so what happens is white is very unstable. Pretty sure in the lecture it says there's a 60 degrees angle between the phosphor. So I'm just going to draw a random structure here, maybe here. That. And so what happens here is that imagine it's like a pyramid, and the angle between one of the slant edge and one of the side edge of the base is 60 degrees, and it causes a lot of strain, and so that breaks it up into so you're no longer a sort of a pyramid. You just sort of turned into this square shape. Okay? And they will form bonds and so on. Cool. Yeah, I just leave it as that. Phosphine, hydrides. In this case, there will be positive 3 charge. Oh, sorry, negative 3 oxidation state because they're staying with hydrogen. Okay. And also, again, when we're going through this, make sure note that Si, P, and S can form more than octet. Okay, so oxides, nitrogen. Cool. Yeah, so we have phosphorus. Yeah, phosphorus. Yeah, phosphates, negative 3. Is it phosphorus? Phosphide ion. So one is phosphorus, one is phosphide. Now the oxidation state, 4 times negative 2 is negative 8, plus 3 it is negative 5 here, so you can see it lost, wait a minute, since it, oh, positive 5, sorry. Yeah, positive 5. So maximum state here, negative 2, 3 is negative 6, so it is plus 4. Okay, so plus 4 plus negative 3 plus negative 6 gives you negative 2. Which means it lost all of its p electrons. Okay. Phosphide, you got nitrogen monoxide, nitrogen dioxide, and dinitrogen oxide. And these will be involved. Nitrous oxide, nitric oxide, and nitrogen dioxide. It's brown gas, nitrogen dioxide. So another way to refer to these, the nitrous or nitric, you have a more oxidation state. So the more oxidation state you have, you got nitric, I guess. Yeah. So this one will be nitrous oxide. nitrogenation. One is synthetic, human. One is natural. So that is bacterial nitrogenase. Now you need high pressure, high temperature, and pretty catalyst for the Harvard process. I think we learned that in high school. So okay, I think we can just skip through that. We go lighting. Another different process is, in terms of the lightning, it's a multi-step process. So you start with nitrogen as always. But unlike these conditions here, unlike these two, this reaction involves oxygen. So generally, when we add oxygen, we go up. We go in a stepwise process. So we don't go to NO2 right away. We go to NO. Okay, that's gonna be form 2. I'm gonna do another color. This NO here will add to oxygen, and that's gonna form. And we'll go up another level. NO2. NO2 here. That's fair. And finally, we're gonna add water, because things like nitrogen dioxide, things like sulfur dioxide, when water comes in contact, they will form acid. It means we'll form nitric acid. And now it's not balanced. That's strange. Yeah, we don't form nitric acid right away. We form nitrous and nitric acid. Okay. So nitrous and nitric acid. I'll do that again. So we form these polyatomic ion here. This exact same process not only can occur by lightning, but also in energy combustion. Because what these involves is they have quite high temperature, right? Because lightning is pretty hot, so a lot of temperature. Water time. And this bit here, we're talking about effects on effects on environment. Actually, hang on. Not really. The effects on in this thing here, I have to focus on effects on environment bit as well. So imagination, and I'll probably just go. How do I do this? Okay, split up like that. Split up like that. And I'll probably say effects on environment here. Effects on environment. Okay, so what happens is when nitrogen dioxide is produced, it can interact with UV light. It's going to cause an oxygen atom to be emitted, and that's going to react with the existing oxygen which is in this diatomic form, and it's going to form ozone. ozone would then cause smoke. What is smoke? Okay, smoke. Smoke is air pollution. Okay, so affects environment is nitrogen here. UV light, I'm just gonna go UV light. That's gonna hit, it's gonna form NO plus oxygen. Sorry, plus O. And then O plus oxygen will form ozone, and this has two effects. One, it is toxic gas. Two, forms smoke when reacting with hydrocarbon. And number three, which is actually a positive thing, is it shields us from UV light, so form atmosphere. Okay. Now let's get to the oxides of phosphor. Oh my god. Okay, that's okay. Oxides. So we obviously know that you can be +3 or +5. So this oxide here. Phosphorus actually go through a pretty similar reaction.